Hello everyone. I'm Zhao from Xiamen University of China. In this talk, I will first thank my student Wang Zheng, Wei Chenfu, and my colleague Yuan Zhang, who contribute to this talk. And indeed, we are all together working for several years for these topics. Here is my outline of my talk. In my talk, it will be 3 parts. The first part, I will briefly review some previous studies for one-dimensional lattices. I mean, for the thermalization of one-dimensional lattices. And then I will report our numerical results for 2-dimensional and 3-dimensional lattices. And finally, I give our theoretical analysis of the thermodynamics of classical lattices. So the first part, I think all of you might be understand, maybe know this problem. It is the question is that for a Hamiltonian chain, for a one-dimensional chain, which described by Hamiltonian, here H0 is integrable part of the Hamiltonian, and the second part is the perturbation part. The problem is that for a sufficient perturbation strings, is arbitrarily small nonlinearity enough to thermalize the system. So, in more detail, just a moment. Yeah. In more detail, the problem is that for a Hamiltonian system, when we represent its variables in the terms of normal modes of the harmonic Hamiltonian, I mean, just have these 2 parts. Then the problem is that when we initially set a partition of energy to one mode or several modes, then the question is that with the evolution of time, does the energy will relax to all of the normal modes. So this is the so-called energy equipartition problem or thermalization of classical system. Indeed, there is some subtle difference between the thermalization and the energy equipartition. But in my talk today, I will not distinguish the 2 concepts. So the first part, in the first part, I will show a conclusion. I will try to show a conclusion is that the energy relaxes following universal scaling law like this. So I mean, this law applies in the thermodynamic limit, and so the energy equipartition hypothesis applies for one-dimensional lattices. In more detail, I will try to. Indeed, in this part, I will try to convince you of such a universal law. We know that the energy equipartition hypothesis is at the foundation of static physics. However, around the middle of last century, 2 famous events shaken the confidence to this hypothesis. You know that the first one is the so-called KAM theory, which says that there is some invariant torus, and I mean, that is to positive measure set of invariant terms. So it will provide the energy equipartition. And another evidence is that by Gavin, by Fermi and et al., they performed numerical experiments to the so-called FPU chain, and they put the energy to Y of the mode, and they found that the energy will return to this mode after some time of evolution. So this means that the energy equipartition hypothesis fails for this system. But indeed, before these two events, there is another series, another fundamental series for particularly the Bangla-Fermi theory, which says that there is no invariant manifolds that can divide the phase system of a Hamiltonian system with many freedom, many degree of freedom to different parts. That means the trajectory can diffusion in the whole physics space, in the whole physics space, and therefore the energy equipartition should be reached generally. So from the theoretical part, the energy equipartition can always be reached, but the question is how fast. So a lot of studies include numerical and analysis studies have been attacked this problem. Before I talk further, I would like to introduce several models, several typical models which used to study the thermodynamic problems of one-dimensional systems. The first 3Y is presented by Fermi et al. In the original paper, and the first two terms are the harmonic terms, and if we put a cubic term, cubic perturbation, then you obtain the so-called FPU beta model, and no, not a cubic, a quartic term, but I'm sorry for such a mistake. And if you put a cubic term here, then you obtain the so-called FPU alpha model. And if you put both perturbations, then you obtain the FPU alpha beta model. Another lattice model, which called the 5-4 model, is also applied for this purpose. It also include integrable part, the first three term integral parts, and quartic term, which is an unset quartic term as the perturbation term. So for these typical systems, there are a lot of studies which focus on the problem of thermalization. Here, at least several of them, certainly not include all of them. The first one I want to show is that by these two authors in 1996, which present theory they call the probability theory of resonance of small dating, and show that this is almost analytic, rigorous analysis, which gives which obtained that the FPU beta model at the 5-4 model, for the FPU at the beta model at the 5-4 model, the energy relax follows such a scaling law, such a time scaling law. So here epsilon is the specific energy defined here. Then Professor Lepre used the so-called model coupling theory and found that for FPU beta model, it also follows the same scaling of time, the same time scaling of relaxation, and also Casati et al. Also studied the problem which focused on the FPUT alpha beta model. In their work mainly by numerical simulations, and they obtained that such a scaling law, which is different, which is different from the above two ones for beta model and the 5-4 model. And Benetti et al. Have done a lot of researches to this problem. They also studied the FPUT alpha beta model, but they found that the scaling law is given by this formula, which here you see -502, which is also different from Casati's prediction. And recently, another group has done this, have attacked this problem using the so-called wave turbulence theory. They found for the 5-4 model, the time scaling is given by also such a scaling law, but they applied a slightly different definition of the parameters. So you see, they are scaling, the parallel like scaling law, but with different exponents. The question is that is there a universal law? So my talk and our work is focused for such to answer such a question. The answer may be based on the so-called wave turbulence approach. So this theory indeed proceeded very early, but it is applied to the study of lattice systems. The one-dimensional lattice systems might be by Professor Spahn in 2006, and until recently, this group of authors used to study the thermalization of one-dimensional lattices. Here I summarize the wave turbulence approach to this problem. The first point is that in a P-wave resonance, the energy relaxes as such a polar law, which means if you have a three phonos process, then the energy relax between the three phonos in such a polar law, epsilon minus y. So this is from the fundamental theory of wave turbulence theory. Then this also, as I just mentioned, further present that for organic system, if all of the modes are interconnected by resonance P waves, and P is the smallest integral of resonance forming the interconnected network, then this scaling law should be the scaling law of the thermalization of the whole system. So maybe this is my contribution of the wave turbulence theory to the thermalization of lattice systems. With their approach, for finite-size systems, sometimes the low order non-trivial resonance set cannot form an interconnected network. So in such a case, you should find one should think for interconnected high order resonance waves by using the linear transformations to find the high order resonance. The idea is indeed very simple. For in the case of P-wave resonance set are non-trivial resonance sets, and they are interconnected to form a global network like this. Here is a wave resonance set, and this is a P-wave resonance. This is our wave resonance. This resonance set connected in such a way. Then, if you put the energy initially to this mode, then the energy can be dispersed to all of the modes, all of the normal modes, and the energy equipartition approach it. The wave turbulence theory emphasizes that in this case, the dominant time scaling of the thermalization is determined by the P-wave resonance. And then in the case of arbitrary potential, when you study a real system, then your potential can be independent by the Taylor extension like this. For example, but in the case of finite-size systems, sometimes, for example, although the cubic nonlinear term exists, but the three-wave resonance cannot form a connected network. In this case, you have to think for the high orders until the P-wave resonance can form a global network. Then you find the dominant process, which dominate the relaxation of the system. In such a case, you will find such a parallel scaling. So based on this theory, this also studied the FPU alpha model, FPU beta model, and also the 5-4 model. They found that for short size, for small size systems like this, then the cubic and the force resonance cannot be form a connected network, and the six-wave resonance in all these cases can form the connected network, and therefore for this system with this small size, the energy relax process is dominated by the six-wave resonance. In such a case, follow this formula, we can predict that the scaling law should be look like this, epsilon -4. But this is true for FPU beta model and also for 5-4 model. But if applying different parameters like this, then you might find the scaling law like this. So this result, this is a rigorous result, and therefore which confirms that for the original mode studied by Film et al. The energy equipartition can reach it finally if the evolution time is long enough. But you see, this is for finite system. What about long enough system? I mean, in the thermodynamic limit. Our group in recent years have been focused also on this problem based on the theory of wave turbulence theory. Our result, my result is that for a Hamiltonian system with the H0 to be the integral part, which is most close to the whole Hamiltonian, to the Hamiltonian you studied. And then if you find a proper parameter, find a proper parameter which measures linearly the distance from S0, you can find that the thermalization indeed offers such a universal law. I mean, for different lattices, alpha beta or FPUT alpha model, 5-4 model, etc. So then
may I interrupt you? I have a question. So okay. Here you are not specifying boundary conditions.
Yeah, it's not depend on boundary conditions. Because we are discuss the problem of thermodynamic limit. So theoretical or numerical not depend. The boundary condition does not affect the universal law. Okay, so the came problem is how to determine the parameter G, the perturbation parameter. I mean, for such a Hamiltonian, I will study. I will give you examples case by case. In such a Hamiltonian, I mean, this is a harmonic part. The first two harmonic part, and the last one is a polynomial term, polynomial nonlinear term, but just the nth order polynomial term. In such a case, you can find there is a scaling behavior which can transform the Hamiltonian, the original Hamiltonian, to a normalized Hamiltonian, which is in the unit of specific energy. So for such a Hamiltonian system, by use such a transformation, you find the perturbation parameter of the new Hamiltonian goes by this formula. So, therefore, we think that the Toda G, the parameter Toda G should be a good parameter we search for. Then, if by using such a parameters, I mean, then you can fix G, this parameter G and change epsilon, or fix epsilon and change G, or change both of them, but calculate the values following such a formula. Then you should find all of the modes over such a universal scaling law. So the first example is given by this Hamiltonian. You know, for this Hamiltonian, the perturbation term is a symmetric potential. It's a symmetric potential. in such a case, our numerical result shown here, you see, it is perfected for Albert's universal law, and for this varies for parameters D. I mean, you can put D equals 3 or 7 over 2 or etc. You will obtain the same scaling law. So in such an example, the harmonic Hamiltonian is a good reference, and Toda G is a good perturbation parameters. So, and then the next example is the symmetric or asymmetric potentials, but look like this, but with disordered mass. Here you see the MI, the mass of mass MI is random values from this interval, and in this case, with different n, here we show examples for n equals 3, 4, and 5. You obtain the perfected universal law. So in such a case, the harmonic Hamiltonian is still a good reference, and the Toda G is a good perturbation parameters. Well, however, if for such a Hamiltonian system, but with homogeneous mass, in such a case, if we still reference, still use the harmonic lattice model to be the reference Hamiltonian, then we obtain such a result, which indicates that the scaling law is still polar-like, but the exponents are different for different parameters. So that means if with the harmonic lattice to be the reference, then the universal law will be violated. But a lot of studies, previous studies have made it clear that the FPU beta model, that here is the FPU beta model. For the FPU beta model, the reference integral Hamiltonian not be the harmonic model, not be the harmonic model, but the Toda model. So there was a lot of reference, but Benetti et al. Have emphasized this point. So the reason is simple, because for the Toda potential, by use the Taylor expansion, you find the first nonlinear term is the cubic term, and by properly adjust the parameters of the Toda potential, then this cubic term should be identical to the FPU alpha model, which means that FPU alpha model is should be considered as a perturbation model of the Toda, the perturbation of the Toda model, which nonlinear term begins from n equal 4, the quotic term. So in such a case, we should study the FPU alpha model with the reference of the Toda model, and also for other terms of for other situations with with all the potentials, with all the term potentials, then we should also reference, the reference model should be also the total model. With such a reference, you see, we obtain the perfecting, we recover the, reproduce the perfecting the universal rule. For such a kind of parameters, we show a perfect a perfect agreement to such a universal rule. And the last example for the diatomic toda lattice. The homogeneous toda lattice is an integrable system, but the diatomic toda lattice like this is a non-integrable system. But in such a case, if with the reference of the homogeneous toda model, then we obtain two terms. First term is that the original Toda lattice Toda model, and the another term is the perturbation term. For this perturbation term, we can show that it is proportional to the difference of the mass difference, proportional to the mass difference, which means the mass difference can be applied to a parameter which measures the distance from the integrable system. In such a case, with such a parameters, we see that the universal scaling law perfected, obtained. But if you adopt such kind of parameters, Toda G equal to my over m2, then if my equal m2, then you return to the harmonic, not harmonic, you return to the Toda model. But if you apply such a parameter, you cannot obtain the universal rule. Also, if you directly apply the energy, the specific energy, then you can also not obtain this universal law. So the choice either you have find the proper reference Hamiltonian, the parameters which measures the distance from the integrable Hamiltonian is very important for such a universal law. Then this is the summary of my first part. For one-dimensional lattices, arbitrary small nonlinearity is enough to thermalize a system if the system is large enough. And the thermalization offers the universal scaling law, offers such a universal scaling law for various systems with homogeneous or disordered masses. But the condition is that the H0 you find you should find the integrable H0, which is the most close to the Hamiltonian you studied. And in such a case, you should also find a parameter to which is a linear function of the perturbation part of the Hamiltonian. So then I turn to my second part. The second part have not been reported, but part of them have been set to the ACKNOWLEDGMENTS as appropriate. In these studies, we studied several typical high-dimensional lattices, which include two-dimensional square lattice, two-dimensional hexagonal lattice, and also the three-dimensional simple cubic lattice, also the three-dimensional FCC lattice. All studies indeed first performed by theoretical analysis and then confirmed by numerical studies. But here, I would like to first report the numerical results. For example, we will stand the case with the polynomial perturbation potentials with n equals 3 and n equals 4. I mean that the harmonic part is the usually used harmonic oscillator, the Hamilton of the harmonic oscillators for high-dimensional lattices, and the perturbation part given by this term, by this formula. And here, as an example, we just studied n equals 4 and n equals 4, the two situations. Indeed, our theoretical result not being limited by such a special shortcuts. This result I show you is about the finite-size effect. This plot for the simple cubic lattice in the case of n equals 3. In the case of n equals 3, you're seeing that with the increase of the system size, the result, the equal partition time converges quickly to such a universal curve. In such a case, you find that the result will not change with the further increase of the system size. And also in the case of hexagonal lattices with n equal 4, certainly we have studied other cases, but here for example, I show just the real result for n equal 4. Again, with the increase of the system size, the result converged, and which means with further increase of system size, this scaling behavior will kept unchanged. This result obtained by use fixed boundary condition. If you use a periodic boundary condition, you can also obtain the similar result, but the converged size should be much larger than use the fixed boundary conditions. So by avoid the finite-size effect, I report my results of our studies. You're seeing that for all of these cases, I mean for the four typical models we just mentioned above, and with homogeneous or disordered masses, and with n equals 3 or n equals 4, almost most of the result converges to the universal scaling law, except the case of cubic, the simple cubic lattice and the square lattice. For these two lattices, in the case of n equal 4, just for n equal 4, then you find the divergence in such a parameter range. But even for cubic and square lattices, in the case of n equal 4, n equals 3, then you find the universal law still produced. Then we extend the simulations to more small parameter regions. for the two lattices I just mentioned. For in such a case, you see that in the extremely low energy densities, also weak enough parameter perturbative parameter ranges, the universal law recovered, reproduced. But in the Euro energy density ranges, it is all approximately planes, but there are obvious divergences. Then I will not discuss this effect in detail. I just want to point out that the energy spectrum of the simple cubic and the square lattice have high degeneration degrees. This should be responsible for the effect I just reported. But anyway, for low enough energy densities or weak enough perturbations, all of these modes show universal scaling law of thermalization. So not only the one-dimensional systems, but also high-dimensional lattices follow the same universal law of thermalization. Then we have also studied the model with Lennard-Jones potentials. So the four typical models, the four typical lattices with the Lennard-Jones potential. You know, Lennard-Jones potential looks like this. Again, we found that with the increase of the system size, we obtained the scaling law of thermalization. You see that with the increase of the system size, it converges to a case which corresponding to the three-wave resonance. Which correspond to three-wave resonance. The reason is that, by the way, if we suppose the process is dominated by three-wave resonance, then we can use such a formula to calculate the Toda G. And again, we found that this in all this case, the universal law is also obtained. I mean that for general potentials, the universal law still can be a good approximate. The reason indeed is very simple, because in the Taylor expansion, the Lennard-Jones potential, have the first nonlinear term is not Lennard-Jones, for the Lennard-Jones potential, the first nonlinear term is a cubic term. So follows the wave turbulence theory. In the case of low energy densities, the three-wave resonance should be dominant the system and form an interconnected network. So the high-dimensional systems should be show thermalization behavior, which means the thermalization in high-dimensional system indeed more faster than in one-dimensional case in Euro level. So the last part, maybe I need a little bit faster. The last part is for the theoretical analysis. For theoretical analysis, I would be just introduce briefly, and maybe you can, if you're interested, you can find our people in Aarhus, and maybe several tests later, because the first one is simple and without such a kind of detailed derivations of the thermalization rule. So, but the framework is that first we derive the kinetics equation of normal mode in the framework of perturbation theory. I mean, in the perturbation theory, in the normal Euro perturbation theory. Then a camport is that for such a purpose, we use the so-called generalized Gibbs ensemble, which is a hypothesis, but it's already widely applied in various problems. Then, in such a case, I mean, in the case of thermodynamic limits, the interconnection condition is can be obtained in the framework of wave turbulence approach. With this steps, then we obtain the analysis result, the theoretical results. This slide shows the first steps, which if you have such a Hamiltonian system, such as Euro Hamiltonian system of high-dimensional lattices, then you can expand it around the lattice size, and you obtain the harmonic term. The first two terms are represented harmonic Hamiltonian. The part of harmonic Hamiltonian, and this part represents the perturbation part. The perturbation represents the perturbations, and then by assuming the perturbation, the temperature is very low. Then you obtain the kinetical, you obtain the kinetical equation of the integral of motion. The integral of motion, I mean, is an integral of motion. You obtain the kinetic equation of the integral of motion up to the second order. This is all standard treatment for by using the perturbation series. After you obtain such a formula, then we introduce the generalized Gibbs ensemble, which says that with weak perturbations, the distribution function f can be described by the so-called ensemble, the generalized ensemble, generalized Gibbs ensemble, given by this formula. Then, with this formula, we can obtain such a formula, such a equation, and then introduce the complex normal mode. The integral part of the Hamiltonian will be you can rewrite the integral part, and which gives by this formula, and also you can represent the perturbation part, the perturbation part of the Hamiltonian. Here, for single sample, we just start the perturbations of the given by the nth order nonlinear terms, the nth order polynomial terms. In such a case, then we finally obtained the so-called n-wave kinetic equation. So for this equation, if we assume the coefficients, not it's no vanishing, is not there. I mean, if this parameter is not there, then you obtain the relaxed time scaling of the system, which gives by such a formula. In high-dimensional system, indeed, it is easy to show, to prove this term and also this term. These two coefficients are really not vanished in the thermodynamic limit. I mean, the resonance condition for the frequency and also the resonance condition for wave vectors can be easily proved in the case of disordered system or in the case of homogeneous systems. And also applying the multiple branch, the property of the multiple branch phonos, then we can prove that the interconnect condition can be also easily reached. Then also there is such a transformation for the Hamiltonian, and that therefore we obtain the universal scaling law of relaxation, or the universal law of thermalization, which means for the high-dimensional systems, we can the thermalization, the thermalization behavior is the same for the one-dimensional systems. You know, this is almost the all result of ours. What I want to just mention is that for high-dimensional systems, you know, there is almost few works to have a numerical or theoretical focus on the problem of thermalization or energy equal partitions. Maybe just two of papers we found to have studied this problem. One is the paper of Benetti, and another, I'm sorry, I forgot, but I have listed the reference in one of my slides. Then this is my conclusion. For the high-dimensional lattices, generally they are always a universal thermalization law, and it seems that the harmonic model can be generally served as the reference Hamiltonian, which means you see in such a, for these results, we not only include the case of n equals 3, but also n equals 4. In the case of n equals 3, in the case of one-dimensional system, we have emphasized we should use the Toda lattice as the reference of the integrable Hamiltonian. But here, for the high-dimensional lattices, with the harmonic Hamiltonian as a reference, we obtain the universal law. So for high-dimensional systems, the situation is quite simple. The integrable Hamiltonian is just the harmonic Hamiltonian. And another point I want to emphasize is that in high-dimensional system, the three-phonal resonance is not forbidden. You know, in one-dimensional case, for some models, for some homogeneous lattice models, the three-phonal resonance is forbidden. And in high-dimensional systems, it is usually allowed. And so the thermalization of real world two-dimensional and three-dimensional indeed follow such as scaling law. So the following such as scaling law in terms of energy densities, which means the high-dimensional system can be easily thermalized. Another question remind is that we have found that degenerates might enhance the thermalization and also can change slightly the decay laws of thermalization. But this problem need to be further studied, and I have little information about this part. Okay, thank you very much. Yeah, questions is welcome, but you know, my English is not good, so when you ask questions, please speak slowly.
Thank you, Gonzalo. Thank you very much.
Thank you.
Do we have any questions? Yes, please, Felipe, go ahead.
Yes, hello. I wanted to ask about if you have an idea of a criterion to choose the closest integral Hamiltonian, or how will you do it in more general cases or different cases?
Yeah, that's a good problem, but frankly, I have no idea in general to find a Hamiltonian system which Hamiltonian system is the most close to the Hamiltonian you studied. Because we know in one-dimensional system case there are just several integrals Hamiltonian, so you can try. And when you find the one which obtained the universal scaling law of thermalization, then you can show you find the most close Hamiltonian, integral Hamiltonian. But in the case of high-dimensional systems, we don't know. I mean, except the harmonic oscillators, we don't know which if there are any integral models. So so it seems for high-dimensional systems, the harmonic oscillator model should be good for every lattice models.
Okay, thank you.
Any other question? I don't see any, nor in the chat. So let's thank Hong Zhao again for his talk. Thank you very much.